are two elements in L1 of G, so that these two are Lebesgue integral. Okay. Then for any element in G such as G, we define f1 star f2 of G equal to this integral f1 of H, f2 of G inverse G of H. This Mg is the Haar measure for G, because we consider G is a locally compact group, so we have a Haar measure on G, and this integral take with respect to this Haar measure. Please note that f1 and f2 are two integral functions on G, so that these two are function from G to complex number or scalar field, and f1 star f2 is again a function from G to complex number. And we have these very important properties, that this function is a Lebesgue integrable function too. Okay, let me write this for you. Let G be a locally compact group, and M of G be the Haar measure of G. Okay, for every f1 and f2 in L1 of G, L1 of G is the set of all f from G to C, such that integral is finite. Okay, we define f star G for f1 star f2 of G or X equal to the integral of f1 of y, f2 of y inverse x, d of mg of y for any x in our group G. and I say that this integral is with respect to our hard measure and by this variable y, so that this is a function with respect to x. Okay, and this is very important that for any two elements in L1, F1 star F2 is an element of L1 2. Okay, F1 star F2 is an integrable function. This is this proposition. Furthermore, L1 with this binary operation is a Banach algebra. This is a binary operation. Okay, this is a binary operation because a function from L1 times L1 to L1. Okay, so that this is a binary operation. Now L1 with this binary operation is a Banach algebra. Muhammad, you have my voice? You recall that I say in any Banach algebra, in addition to addition operation and scalar multiplication, we must have another binary operation. This is this binary operation. You can see the proof in many books. And I recall again that L1 of G is the set of all f such that this integral is finite, and the norm of this vector space is this finite real number. Definition: let X with this norm be a Banach algebra. A left approximate identity for X is a net such as this in X such that we have this equality for each X in X. This limit must be equal to 0. This is a net in X. Okay, please note that X alpha is an element of X, and X also is an element of X, and we have this multiplication in X because this is a Banach algebra. If we consider, for example, a star as the binary operation of this Banach algebra, in this equality we must write X alpha S star X, okay? X alpha S star X minus X. This known in X must be 10 to 0. And this net is called bounded if there exists a positive real number such as m, such that for any alpha this known be less than or equal m. Okay. And also similarly, if we have a net such as x alpha such that this limit equal to 0, x S star X alpha, not X alpha S star X, then this net is called a right approximate identity, and this approximate identity is bounded if we have this property again. Now if we have a right and left approximate identity, we say that this is an approximate identity, so that an approximate identity is a left approximate identity and a right approximate identity. And also we have this theorem L1 with convolution operation. This S star is called convolution, okay, has a bounded approximate identity. Or equivalently, there exists a net such as E alpha such that for any integrable function such as f, the limit of E alpha star f minus f and the limit of f star E alpha minus f tend to 0. Okay. In this Banach algebra, or binary operation is a star, or multiplication is a star, convolution. Note that M of G, the algebra of all Borel regular measures, is a Banach algebra that have an identity. Indeed, if E is the identity element of G, then Dirac measure at E is the identity element of M of G. So M of G is unital Banach algebra. Is a unital Banach algebra. Okay. For this, delta of E is the identity element of M of G. We only must use the definition of convolution in measure algebra. For any mu and mu in M of G, we know that mu star nu is this functional on C0 of G by the Riesz representation theorem. mu star nu of f equal to this integral. Now if we consider, for example, this nu equal to Dirac measure at E, we see that nu equal to delta of E equal to this integral or this integral. And we know that this integral equal to, you must put instead of by E, so that this internal integral equal to f of xe and equal to x, so that this is equal to the integral of f d mu, or mu of f is solved by the Riesz representation theorem. So that for any f in C0 of G, mu star delta E of f equal to mu of f for all f, so that these two functions must be equal. Okay. And also for any f in C0, we have this equality, so that mu star nu equal to mu. By this, we conclude that mu star delta E equal to mu, and by this we see that mu star delta E equal to, so that okay, I write this so we can omit this. Similarly, we have delta E star nu equal to mu. Therefore, delta E is the identity for M of G. Is the identity for M of G. And I recall again that for any Dirac measure is an element of M of G, so that must be belong to the dual of C0 of G. In C0 of G, delta x of f equal to f of x, and also C0 G prime is the dual of C0 of G by this definition. Okay. And this equality obtained easily because if we consider For example, f equal to this characteristic function, consider f equal to this characteristic function. Okay, then we know that this integral equal to delta x of e, and this is equal to e of x, so that we have this equality for characteristic function. Now to a simple function. A linear combination of characteristic function, then the integral of this f, these functions with respect to this Dirac measure equal to delta x of this, and this is equal to this summation, and this is our f of x, so that this holds also for simple functions. And in the first step we have this equality, because for any s measurable function there is a sequence of simple function by this property. Okay, so that for Dirac measure we also have this equality. For this reason we write in the proof of this proposition this internal integral equal to f of x e. We put instead of y equal to e. Okay, and please note that m of g is a Haar measure. Okay, m of g is a Haar measure. Haar measure. So we have this equality for any g in G and for any Borel subset of G, mg of GE equal to mg of E. This measure must be left invariant, but this measure is not necessarily right invariant. Mg of Eg is not generally equal to mg of E, but we have a coefficient such as delta G for any G in G and for Borel subset of G, mg of Eg equal to delta G of G, mg of GE is this left coset and EG is this right coset. Okay, now if G be an abelian group, then for any E in beta and G in G we have GE equal to EG because G considered abelian. Okay, so in this case, this function must be equal to 1. This function is called the modular function of G. Modular function, okay? This is the modular function of G. Modular function of G, okay? We can consider if in any locally compact group G, delta of G equal to 1, we say that G is unimodular. G is unimodular. So G is a unimodular group. Okay, unimodular group. Unimodular group. Okay, we can consider L1 of G as a subset of M of G. L1 of G is the set of all integrable function on G and M the major algebra. This is called the group algebra and this is called the major algebra. Okay, let me write this for you. Let me write L1 of G is called group algebra. Now we say that L1 of G can be considered as a subset of M of G. Group algebra is a subset of major algebra. Please note that any element of L1 of G is a function such as f from G to C, but any a function from B to this interval, so that these two space have different elements, but we can embed this set to this set or this space to this space. This is very important. This is the group algebra and this is the major algebra. The element of this space are functions from G to C, and the elements of this space is measures from beta to this interval. Okay, these two is not the same. And the domain and range of these two functions is not the same. But we can embed this to this. Let we define a function such as h from L1 to m of g by this function rules. H of f equal to mu of f, such that mu of f is this measure mu of any Borel set equal to the integral of f on this Borel set. Okay, by this we construct a measure on G for any Borel subset of G. We define mu f of f, mu f of e equal to this integral, so that mu f is a function from beta to c. It is not difficult that this is a measure and this is belong to m of g. Okay, then mu f is a measure in our measure algebra. Okay, so that and also we have these properties for any f in L1 of G, L1 of G the norm of h of f equal to the norm of 1. This shows that h is 1 to 1. Okay, so that this is a linear and 1 to 1 functions, so that this set embed in this set. Please note that, dear students, this is very important that it is very important that if H, for example, from A to B, is an one-to-one function then H from A to H of A, the range of A, okay, as n subset of B. If we consider this function from H to the range of H, not whole of B, is a surjective function. Okay, this function is one-to-one and onto, so that this is surjective. And this shows that and of A are in the corresponding, or in the one-to-one corresponding, but important that it is very important that this A is in a one-to-one corresponding by H of A, and H of A is a subset of B, so that we can consider A as a subset of B. Okay, or we can write we embedded A to B, we embedded. Okay, notice these two are algebra and this H is a homomorphism. This is an algebra again, so that this A is a subalgebra of B. This A can be considered as a subalgebra of B. And in this proposition, we have an one-to-one function, because we say that this is an isometry. Any isometry is one-to-one. Any isometry is one-to-one. So that we define a one-to-one function from L1 to this. So L1 can be embedded in M of G. L1 is a subset of M of G. Please note that any if H from A to B, for example, is an isometry, then H is one-to-one. Okay, 1 to 1, because if h of x, for example, equal to h of y, then the norm of h of x minus h of y equal to 0, and this shows that the norm of h of x minus 1 must be equal to 0, because h consider linear function, and this shows that this norm must be equal to 0, because h consider an isometry. H is isometry, okay, and this shows that x must be equal to y, so that if h of x equal to h of y, x must be equal to y. Any isometry function must be 1 to 1. In this case, we have an isometry function, so that this function is 1 to 1, and so this group algebra embedded in this measure algebra. This measure algebra. Okay. Okay. By another approach, we can embed this group algebra to this measure algebra. This is another proof, okay, or another approach. We can define another function such as h prime. H prime from L1 of G of G, that G do by their theorem representation in L1 of G, h prime of f as an element of this dual is this function h prime of f of h, because it is so what this function must be act on function in C0 of G. H is in C0 of G. We define this function by this equality. Is equal to the integral of fh of f, the integral of fh dmg, or the integral of h with respect to d of mu f. Mu f defined in the previous slide, okay? Please note that if we consider f in this vector space, then h prime of f belong to this dual, so that h prime of f is a function from c0 of g to c. Okay. For any f in the group algebra, h prime of f is a function from the dual of c0, so that h prime of f is a function from c0 of g to c. We can check that h prime of f is a bounded and linear function on c0 of g. Okay. On c0 of g. So h prime of f is in the dual of this space c0 of g prime, the dual of c0 of g. So for the definition of h prime of f, we must define h prime of f on all elements in this space. All elements in this space. H prime of f of h equal to the integral of fg with respect to our Haar measure m. And we say that h prime of f is a bounded and linear function on c0 of g, so that this is an element in the dual of this space. And this is a well-defined function, and we can embed L1 to m of L1 of g to m of g. Okay. This function is linear and again isometric, so that we can embed this space to this space or to this space. But we use this equality that you can prove this equality S star prime. We prove this in the next okay, we use in the following. We use this equality in the following. The proof of this very easy. By the definition of mu of f, you must consider at the first characteristic function, then simple function, and then arbitrary measurable function. Okay. And we have also this definition: if mu and nu are two measure in our measure algebra m of g, we say that mu is absolutely continuous with respect to nu whenever for any e in beta. If mu of e equal to 0, we can conclude that mu of e equal to 0 too. If mu of e equal to 0, mu of e equal to 0. If this property is false, we write mu is absolutely continuous with respect to mu. Mu is absolutely continuous with respect to mu. If mu of e equal to 0, then mu of e must be equal to 0. For example, for any integrable function such as f, mu of f is absolutely continuous with respect to or Hall measure m of g, because if mg of e equal to 0, then mu f of e or this integral must be equal to 0. You know that this integral equal to this. This is a star prime, okay? This is exactly a star prime. This is a star prime. The integral of h with respect to mu f equal to the integral of hf with respect to m or Hall measure. And this integral equal to this integral, but mg of e equal to 0, so that this integral equal to 0. So if mg of e be equal to 0 is equal to 0, then mu f of e must be 0, so we have this relation. Because we know that in any measure space is a mu, and any f in L1 we have mu of e equal to 0, then this integral on e must be equal to 0. And we have this in this proposition. We prove that any integrable function have this property, that is absolutely continuous with respect to or Hall measure. Conversely, any absolutely continuous measure with respect to m must be integrable, so we have this equality. L1 of g exactly equal to the set of all measures in all measure algebra m of g, such that we have this relation mu is absolutely continuous with respect to m of g. And L1 is an ideal of m of g. L1 is an ideal in m of g. More precisely, if f belongs to L1 of g and mu be in m of g, then f star mu is an element of m of g. and also mu star f is an element of M of G. L1 is an ideal, and L1 is the set of all absolutely continuous measures with respect to our Hall measure M of G. Okay, these are the important properties of group algebras and its relation with M of G, the measure algebra. And for these two, mu star f and f star mu, we have this definition. Mu star f define in this page, mu f equals star the measure, and we know that the definition of convolution of two measures, if mu and nu are two measures, we have this definition: mu star nu of f equal to this equality. Now, if mu belong to M of G or measure algebra and f be in group algebra, what is the definition of mu star f? Because this is an measure and this is an integrable function. But we know that all integrable functions are in M of G, so that you can consider this as a measure by mu of f, okay, by mu of f. So we define mu star f equal to mu star mu f. Okay, let me continue in the next session. Okay, let me continue in the next session. Dear students, do okay, thank you very much, thank you very much, and goodbye for now.